Hello everyone. I would like to talk about our work titled Correlation, our active learning for surgery video segmentation in this presentation. As a context, we had a video dataset on which we wanted to select frame to annotate. For this, we used active learning. At first, we chose a very popular active learning method that is based on uncertainty. This method calculates the entropy for all the frames in the videos and return the frames with the highest entropy to the annotator so he can label them. Um when we apply this method on one of our video that you can see on this slide, it happened that the frames that were selected for labels were the green with the one with green borders. So the problem here is that even though those frames have a very high entropy, they all look similar visually. And this is a problem because we are wasting annotation to basically annotate the same image. So we wanted to design a method that can take into account the correlation that exists between video frames. Our idea is that at first, before calculating the entropy for all images, we will cluster together images that look similar to each other. So we cluster all these similar looking images together, and from each of these different clusters, we will pick the frame with the highest entropy. This way we can get visually diverse image that still have high entropy, and I'd like to think that those frames are maximal local maxima in terms of entropy value. Then in this slide I will detail how our method works to create the different clusters and then sample the frame with the highest entropy from each clusters. So at first we have our dataset from which we labeled a small subset at the beginning and then with this small subset we train our segmentation model on it, and then after the model is trained we leave it aside for later. We pass our label images and unlabeled images to an embedding function that will output a embedding vector for the unlabeled image and our labeled image. Then we put together all those embedding and feed it to a k-means algorithm so it can create different cluster for us. So the idea with the k-mean is that the k, we will choose it to be equal to the number of label frame that we have plus the number of new label that we want to sample. In this example here, k-mean output 4 clusters. So in this case, we have 2 label frame and we want to add 2 more frame to our label set. We have the 4 clusters here have the centroid represented by the cross. The position of the label frame in the latent space is represented by this blue dot. In the next step, we will move the centroid of these 2 clusters to those blue dots. After the centroid of these 2 clusters has been moved, we will enforce that those centroids do not move again, but elements can still go out and go in those blue clusters. So for the next step, we will do another step of k-mean. So I will refer to these blue clusters as fixed clusters, meaning that the centroid cannot move anymore, and I will refer to these red clusters as non-fixed cluster as the centroid can still be updated. So with the second k-mean run, we have a newly updated clusters. So we can see that some elements were added in the blue cluster, but the centroid of the blue cluster remained the same. In contrast, for the red cluster that are non-fixed, the centroid can still move and element can still go out and going. So after this, the second k-mean have converged. The idea is that all the element inside these blue clusters should be visually similar to this labeled image, and likewise all the element in this blue cluster should be similar to this blue to this label image. And then all the image that are in red clusters are normally unlabeled images that do not look similar to any of the already labeled image that we have here. And then from here, we can go inside those red cluster and pick the frame with the highest entropy that are represented by the red dot here. Then after we have selected, and we pick one frame per red cluster, and so we move those two label frame those two unlabeled frame for the annotator to annotate. After annotation, it will be added to the label set, and we retrain the segmentation model on the new label set. We have tested our method against several existing active learning methods on 4 datasets. First, the monarch dataset is the dataset that we showed at the beginning with the bronchoscopy surgery. And then Endovis A2D2 parrots are all public dataset. Parrots is a subset of video from YouTube VOS. Our method titled COWAL is the magenta colored curve. As we can see, in general, it stands above the other methods. Then and it means that our method can achieve higher test performances with fewer annotation that's needed. So this is a qualitative evaluation of our method. Quantitatively, we compare the performance of each method using the area under the active learning curves. So the value for the previous curve are presented here with the ResNet 15 backbone. So COWAL has the best performance of 3 of the 5 datasets and achieves second best performance on the other 2 datasets. On average, he achieved the best evaluation metric here. Now we would like to validate if the behavior of this selecting of this active learning sampling method is as we expected in the beginning, which is that entropy should be sampling all redundant frame, and that our method should solve this problem of redundancy sampling. So in this case, we are looking at the image sample by different active learning method for the monarch dataset. In red, we have the image sampled by entropy. As we can see, there are some redundant image here. And in our case, in the case of COWAL, we can see that this redundancy is reduced, but our method can still manage to sample high entropy images. We can see the same behavior for the Endovis dataset, and we get some redundant frame here for entropy. And for our method, this redundancy disappear, and we still keep the high entropy aspect of the sampling. We can see also for methods such as core set or temporal coverage that they also manage to sample visually diverse frames, but these methods are not specifically designed to sample entropy method, and that could explain why they are not doing as good as our method on the evaluation metric. So in conclusion, we propose a novel active learning approach for video segmentation, which focuses on sampling visually diverse image but still have a high entropy. We compared our method against many existing active learning methods on 4 different on 4 different video datasets, and we visually validated the behavior that our method should have, which is to sample diverse images. Thank you very much for your attention.